Welcome to the debate. Today, we are looking at a shift in perspective that is so fundamental, it actually requires us to unlearn, well, about 2 centuries of medical dogma.
Good to be here. And yeah, it's a massive paradigm shift.
For pretty much all of human history, or at least since we discovered the microscopic world, humanity has been at war. We viewed the virus as the ultimate antagonist. It's the agent of plague, the destroyer of cells, the thing we scrub our hands to avoid.
Right, it's the enemy.
Exactly. But the material we are analyzing today asks us to flip that completely upside down. What if the virus isn't a monster? What if it's actually a courier? Think of it like a molecular truck that we just haven't learned how to drive yet.
It is a provocative thought. We are talking about viral nanites. This is the concept that we can strip the malicious code out of a virus, keep the shell, the chassis of the truck, to use your metaphor, and use it to deliver instructions that reprogram human biology.
And this leads us to the central question we are debating today. Is humanity ready to transition from merely treating disease to programmable evolution? Are we ready to stop enduring our biology and start debugging it like software, eventually rewriting our own genetic code? I represent the position that disease is fundamentally an information failure. Cancer, autoimmune disorders, genetic defects, these are not mysteries. They are corrupted lines of code. And by repurposing viruses as delivery vehicles for corrective DNA, we can cure the incurable and eventually enhance human capability.
And I represent the position that while the technology is undeniably powerful, treating biology like software is a very dangerous category error. Living systems have off-target effects that software simply does not. The cost of this technology threatened to create a permanent biological caste system, and the risks of runaway biological code are frankly existential.
Let's get right into the thick of it then. My position is rooted in the nature of DNA itself. We need to reframe how we see disease. When a person gets cancer, it's not just bad luck. It is a corrupted loop in the cellular program. Growth signals get stuck on, and checkpoint protocols fail. It is, by definition, a software malfunction.
That is a very clean metaphor. But biology is messy. It's wet, it's chaotic, and it's highly interconnected.
But the mechanism for fixing it is already here. A virus is nature's perfect nanite. It is a shell optimized over billions of years of evolution to do one thing, which is deliver data into a cell. It is the most efficient injection system on the planet. If you strip away the viral DNA that makes you sick and replace it with therapeutic DNA, you turn a destroyer into a healer. And consider the medium we're working with here. DNA is the densest information storage known to physics. 1 gram of DNA can theoretically store over 200 petabytes of data.
That statistic always blows my mind.
It's incredible. That is more than all the digital photos on Earth stored in a single gram. We are moving toward a world where we write therapeutic programs into this medium, load them into a viral nanite, and patch the human body just like you patch an operating system.
I see why you think that. And the density of DNA is an impressive statistic, sure. But I am not convinced by that line of reasoning because it completely ignores the implementation. You say software malfunction, but a body isn't a laptop. You can't just Control-Alt-Delete a tumor without consequences. When you introduce these nanites, even stripped-down viruses, you are triggering immune responses. You are navigating a system that has spent eons learning to reject foreign code.
But we are getting much better at evading that detection.
Better, perhaps, but at what cost? We have to look at the economic reality. You talk about this as the future of medicine, but look at Casgevy, the CRISPR treatment for sickle cell that was approved back in December 2023. It effectively cures the disease, yes, but it costs approximately $2.2 million per patient. If we treat the body like software, we are currently charging a premium that 99% of the species cannot afford.
Well, innovation always starts at a premium. The first computers were massively expensive too.
A computer doesn't determine if you live or die. And beyond cost, there's the complexity risk. Debugging code you wrote yourself is hard enough. Debugging code written by 3 billion years of evolution, which we still don't fully understand, risks introducing new errors. You might patch a gene here
and accidentally trigger a cascade failure somewhere else.
I think you are underestimating how far we've already come. This isn't theoretical anymore. We aren't just talking about concepts, we are talking about actual cures. Look at the rapid success of adeno-associated virus, or AAV vectors. As of 2024, 7 AAV products were already approved.
Approved, yes, but for very narrow indications.
Narrow but profound. Let's look at the evidence. You mentioned Casgevy. In the clinical trials, 29 of 31 patients were free of severe pain crises for at least a year. That is a life-changing result for people who were in absolute agony. Or look at NTLA-2100. This is an in vivo CRISPR therapy for amyloidosis, which is a fatal condition where proteins build up in the heart and nerves. Phase 3 trials showed a greater than 90% reduction in the pathogenic protein. We are already patching genetic errors. The code is being rewritten in living patients, and it works.
I am not denying the successes. The reduction in transthyretin protein in the NTLA 2001 trials is remarkable science. However, I come at it from a different way. You are celebrating the vector, but the vector is the bottleneck. The liver is a massive filter. It loves to eat these viral vectors. That means you have to pump in huge doses just to get enough payload to other tissues, which severely spikes the toxicity risk.
Which is exactly why we are engineering better capsids.
But it's not just the capsids. Look at the Cleveland Clinic and American Heart Association trial from November 2025 regarding CTX310. They achieved a 50% reduction in LDL cholesterol, which is a fantastic result. But how did they deliver it? Lipid nanoparticles. They moved away from the viral vector for that delivery. Why? Because the immune system attacks the courier. If the virus is nature's perfect nanite, why are we wrapping it in fat bubbles to sneak it past the body's defenses? It shows that the viral nanite isn't a magic bullet for everything. Biology fights back.
That is a fair critique of first-generation vectors. But that's an engineering hurdle, not a fundamental wall. We are iterating. And this brings me to the architecture of the nanite itself. We aren't just throwing viruses at cells anymore. We are designing a 3-mode architecture. This is detailed clearly in the source material, and it fundamentally changes the risk profile.
Walk me through the 3 modes, then.
Right, so imagine a viral nanite with 3 distinct operating states. First, seek and destroy. It identifies markers of cancer cells, specific mutations, and delivers a payload that triggers apoptosis, or programmed cell death, strictly in those cells. Second, restore mode. It activates regeneration pathways to fix the damage. And third, and most importantly, self-destruct mode.
The kill switch?
Exactly. Once the nanite completes its mission, it deactivates, it shreds its own instruction set. It leaves no trace. This modularity turns medicine into an engineering discipline. We can govern exactly when and how the therapy acts.
That is a compelling argument, but have you considered what happens when the self-destruct mode fails? You're talking about introducing a self-replicating or at least self-sustaining agent into the body. If that kill switch has a bug, and all software has bugs, you risk runaway expression.
The kill switches are triggered by external signals or time-limited promoters. It's not just a timer. It's a structural dependency.
In a lab, sure. But in the chaotic environment of a human body, if a nanite designed to stimulate cell growth fails to turn off, do you know what you have created? You've created a synthetic tumor. You have essentially engineered cancer. This is why I argue that we need safeguards as first principles. These fail-safes cannot be afterthoughts. They need to be triggered by external signals like a pill you take that allows the nanite to function, and if you stop the pill, the nanite dies. Because a bug in this code isn't a blue screen of death. It's actual death.
I agree on the safeguards, but let's look at the potential of that restore mode you sort of glossed over. We are talking about regeneration, the ability to regrow lost tissue.
We are humans, not salamanders. We scar. We don't regenerate.
That is where you're wrong, or rather, that's where the data suggests we might be wrong. We are seeing evidence of a blastema blueprint in humans. A 2025 study from Harvard published in Cell linked adrenaline and systemic priming to limb regeneration in salamanders. It turns out the nervous system creates a body-wide memory of the injury.
And you think we can replicate that?
we might not have to replicate it from scratch. A 2024 study from LSU suggests that humans still possess the dormant genetic toolkit for regeneration. The genes are there. They are just silenced. We don't need to splice in alien DNA. We just need to unlock the code we already have. A viral nanite could deliver the specific transcription factors to wake up those sleeping genes.
Just unlock the code. That word "just" is doing a lot of heavy lifting. Regeneration isn't a single switch. It is a symphony. It requires nerve signals, positional information so the arm knows to grow a hand and not a foot, and intense immune modulation.
But the blueprint is in the library of our DNA.
Reactivating dormant developmental programs in an adult body is incredibly risky. Those programs are dormant for a reason. Adult cells have checks and balances to prevent them from acting like embryonic cells. If you turn on uncontrolled growth and rapid division in an adult, you are again flirting with the definition of cancer. Biology is context dependent. A gene that builds an arm in a fetus might build a tumor in a 50-year-old.
It's a risk, absolutely, but one managed by the precision of the delivery. And this brings me to the next horizon, which I know you are highly skeptical of: augmentation.
Augmentation. Here we go.
We are moving toward functional translation. This is the idea that we can borrow traits from other species, not by transplanting tissue, but by reading their code and writing a human-compatible version.
You mean like the tardigrade?
Exactly, the water bear. These creatures can survive the vacuum of space and massive radiation. They produce a protein called DSUP, damage suppressor. A study from MIT in February 2025 showed that we can deliver mRNA encoding this DSUP protein into human tissues. It binds to the nucleosomes and physically shields the DNA from radiation damage.
I've read the study. It reduced DNA fragmentation by about half.
Think about the implications of that. This enables safer cancer radiation therapy, protecting the healthy cells while nuking the tumor. It opens the door for long-term space travel. Or look at diving mammals like seals. They have optimized hemoglobin for oxygen efficiency. We could identify those genetic modules and update human biology.
This is the library of nature concept.
Yes, it's not magic, it is biology repurposed. We can install night vision using infrared options found in other species. We are talking about upgrading the hardware of the human body.
I'm sorry, but I just don't buy that it stops at safer space travel. You are opening an economic Pandora's box. You mentioned the predator analogy in the source material, absorbing traits to evolve. It's apt, but it's terrifying from a societal standpoint.
Why? It's evolution by choice, not chance.
Because of the horizon problem. If we can install radiation resistance or night vision, who gets these upgrades? We already established that Casgevy costs $2.2 million. If these enhancements follow the same market logic, we are heading toward absolute biological stratification.
We can lower costs over time.
Can we? Or will we create a split species? The physiological halves, who are resistant to cancer, can see in the dark and heal like Wolverine, and the have-nots, who are left behind in the genetic lottery. It is a potential dystopia. If a wealthy elite can literally rewrite their biology to be superior, the concept of shared humanity evaporates. And unlike a luxury car, you can't just repossess a genetic upgrade. Once it's in the germline, it's there forever.
That is exactly why we need governance. But we cannot let the fear of inequality stop the pursuit of progress. The potential to end suffering, to end the lottery of genetic disease, is too great. We are talking about turning the body from a fixed vessel into a living canvas.
A canvas is a nice image, but you can scrape paint off a canvas. You can't scrape a modification out of the human germline once it spreads.
That's why we focus on somatic editing first. Changes that don't get passed down.
For now, but the temptation to make it permanent will be irresistible.
I see your hesitation. I do. But look at the history of medical intervention. We used to be terrified of organ transplants. Now they are routine. We are moving from enduring our biology to authoring it. Yes, we need safeguards. Yes, we need the 15-year FDA surveillance protocols that are already in place for CRISPR, but we are standing on the edge of a new era. We can identify the genetic modules for a desired trait and encode a synthetic version tailored specifically for us.
It is the ultimate hubris, though, to think we can write the code better than nature.
Nature is blind. Nature is slow. Programmable evolution is intentional. We can fix the errors nature left behind.
Or we can introduce errors nature was wise enough to avoid.
That's the debate, isn't it? But the tools are in our hands. The AAV vectors, the CRISPR editors, the knowledge of the D-soup protein, and the blastema. We can't unknow this.
No, we cannot. And that brings us to the reality of the situation. The quill is indeed in our hand. We have the ink, the viral nanoparticles, the Cas9 proteins. But we must be terrified of that ink. The technology to rewrite humanity is here. It is not science fiction. But without massive cost reduction and global ethical frameworks, real ones, not just suggestions, we risk fracturing the species.
And I would argue that while the risks are real, the moral imperative is to write a better story. We are moving from a species that is a victim of its DNA to one that is its architect. We are transitioning the body into a platform for continuous updates, as customizable as software and as resilient as life itself.
It is a beautiful vision, provided we don't write a tragedy by mistake.
The question is no longer if this will happen. The technology is approved, the trials are active. The question is how we will choose to write the next chapter of human evolution.
And who gets to hold the pen?
Indeed. Thank you for listening to The Debate.
Goodbye.
Okay, so let's just dive right into this. I want to start today with what is honestly a bit of a branding problem.
A branding problem.
Yeah, I
Okay.
mean, it's a word that arguably has the absolute worst reputation in the English language right now.
I think I know where you're going with this.
Right, well, for most of human history and definitely for the last few years, this single word has been entirely synonymous with invisible threats.
Oh.
We associate it with fear, with locked doors, with failing economies, or even just, blue screens of death on our computers.
The word is virus.
That word is virus, exactly. When I say virus, the listener's brain likely goes straight into defense mode. You picture the spiky little ball invading your system, whether that system is your lungs or your laptop, and just wrecking the place. It is like the ultimate antagonist in the story of life.
It is. And that's a completely rational evolutionary response, by the way. We are literally hardwired to fear the viral. Our immune systems have spent millions of years learning to recognize and destroy them. But, and this is where we really need to flip the script immediately.
Yeah.
That fear is based on the payload, not the vehicle.
Right. The payload, not the vehicle. And that distinction is basically the entire foundation of this deep dive today.
Yes.
Because what if the virus isn't actually the enemy? What if the virus is just a delivery truck? Arguably the most efficient delivery truck in the known universe.
Yeah.
And for millions of years, it's just been delivering the wrong package.
Exactly.
Today, we are talking about what happens when we swap out that package. We are talking about hijacking the hijacker.
That is the core question here. If you strip away all that history of plague and sickness, a virus is just a tool. It is a molecular courier. If you look at a virus under an electron microscope, or rather if you look at its schematic list, it is arguably the most elegant machine in all of nature.
So simple, right?
Incredibly simple. It's a protein shell called a capsid, which is essentially just a perfectly geometric box. And inside that box is a set of instructions, DNA or RNA. That is it. Its entire existence is dedicated to one single mission: protect that data, bypass the body's firewalls, cross the cell membrane, and inject those instructions into a cell.
So it's a USB drive, a biological USB drive.
Precisely. It's a USB drive that has spent 3 billion years figuring out how to bypass every single firewall your body has. It knows how to navigate the chaotic environment of the bloodstream. It knows how to trick the cell receptors into opening the door, and it knows how to get its data into your hard drive, which is your nucleus.
But the problem historically is that the data on that drive has been something like make more viruses and kill the host.
Malicious code.
Pure malware.
Pure malware. But the aha moment that is driving everything we're looking at in this deep dive is so simple. The danger isn't the vehicle. The danger is the code.
Correct.
So the mission we're exploring today is this. What happens if we strip out the bad code, the sickness, the replication instructions, and we replace it with helpful instructions? What happens when the virus becomes a nanite of healing?
You literally turn the destroyer into a builder. And this reminds me so much of that concept from those Predator movies, which I know sounds kind of ridiculous, but stay with me here.
No, it works perfectly, actually.
But because the Predator doesn't just hunt for fun. It improves itself. It takes traits from other species it defeats to become a better apex predator.
It is a surprisingly apt analogy for the science we are looking at in these sources. We are moving away from a medical paradigm where we just try to survive the hand nature dealt us.
Yeah.
We are moving toward looking at the rest of the animal kingdom, this incredible library of nature, and saying, I want that trait. I want the tardigrade shield. I want the salamander's arm. And instead of grafting tissue like Dr. Frankenstein, we are just copying the source code.
So here is the map for this deep dive. We are going to treat disease not as a biological failure, but as corrupted software. We are going to look at the hardware, the DNA storage, and those viral delivery systems. Then we're cracking open that library of nature to see what superpowers are actually on the table right now.
And we're talking about everything from radiation resistance to literally night vision.
Yeah, night vision. It's wild. And finally, we'll talk about the transition from random evolution, which is slow and messy, to programmable evolution, which is intentional.
But of course, with great power comes terrifying bugs in the code.
Oh, yeah. We will definitely get to the risks, the ethics, and the potential for this like horrific biological caste system. But let's start with the hardware, because when we talk about reprogramming biology, it usually feels like a metaphor. But looking at these sources, it seems you mean that quite literally.
It is absolutely literal. And to understand why, you have to wrap your head around the sheer storage capacity of DNA.
Yeah.
We tend to think of DNA as this mystical blueprint of life, like a spiritual concept almost.
Right, like the essence of who we are.
Exactly. But in pure physics terms, it is simply a storage medium. And it is the densest information storage medium in the known universe.
Densest is a really strong word there. How does it compare to, say, like the best solid-state drives we have in huge data centers right now?
Oh, it makes a solid-state drive look like a stone tablet. Let me give you a number from the research. 1 gram of DNA.
1 gram.
A pinch. A literal dusting. Theoretically, that 1 gram can store over 200 petabytes of data.
200 petabytes?
Yeah.
In a gram?
Yes. To put that in perspective, that is more storage capacity than all the digital photos on Earth combined. All of them, in a space the size of a raindrop.
That is, I mean, that's hard to even visualize. That implies that biology is operating on a level of efficiency that our absolute best silicon chips cannot even touch.
They can't, and scientists have already proven that it works. They've used synthetic DNA to encode books, images, short films. They convert the zeros and ones to biological code, the A, C, T, and G that make up our nucleotide base pairs.
So they basically write computer data into life.
Exactly. They synthesize the DNA, put it in a tiny tube, and then later they run it through a sequencer and read the files back with perfect fidelity.
Okay, so if DNA is just a language, and it can store arbitrary data like a short film, then a disease isn't just my stomach hurts or my cells are mutating. A disease is literally just a typo.
Precisely. It is an information problem. If you have a genetic disease, it means there is a corrupted sector on your hard drive. There's a sequence of letters that is out of order. If you can access that sector and overwrite the typo, you don't just treat the disease, you debug it. You resolve the error at the root.
But here is the logistical nightmare with that. You can't just drink a smoothie full of corrected DNA and hope it somehow finds its way to your heart or your liver, right?
Right.
You need a way to get that data inside the nucleus of the specific cells that are actually broken.
You have 37 trillion cells. You need a courier that can find the right address and break into the house. And that brings us back to our friend the virus.
The delivery truck.
We call them vectors in the industry. And right now the gold standard is the AAV, the adeno-associated virus.
Why that one specifically? Why not the flu or something stronger?
Because the AAV is basically the nice guy of the viral world. It is naturally non-pathogenic. It doesn't cause any known disease in humans. It's small, it's stealthy, and it is incredibly effective at slipping through the door without setting off any of the body's alarms.
How does it do that?
It essentially knocks on the cell membrane, shows a fake ID, and the cell just lets it right in.
Wow. But it's not a one-size-fits-all truck, right? Like, you wouldn't use a massive moving van to deliver a small pizza.
Correct. We have a whole fleet. For example, we have lentiviruses, which are derived from, and wait for it, HIV.
That sounds incredibly risky.
It sounds terrifying. But we strip out all the HIV parts that kill you. What is left is a virus that is a master at integrating code permanently into the genome. You use that when you need a fix that lasts a lifetime. And you have herpes simplex vectors.
Again, the branding on these is just terrible. Here, let me inject you with some HIV and herpes to cure you.
The marketing department really has their work cut out for them. But herpes viruses have a very specific superpower. They love the nervous system.
Oh, interesting.
They are absolute experts at traveling up nerve fibers. So if you were trying to treat a neurological condition, something deep in the brain or the spinal cord, You use a stripped-down herpes vector because it knows the roads. It already has the map.
This is what the papers refer to as tropism, right?
Yes, tropism is the ability to engineer the virus to target specific cell types. Think of it like putting a zip code on a letter. We can engineer the proteins on the outer shell of the virus, the capsid, so that it works exactly like a lock and key.
So it just floats around until it finds the right door.
Exactly. It flows through your blood, bumping into liver cells, lung cells, kidney cells, and it just bounces off. But the moment it touches a heart cell, click, the key turns. It enters.
That precision is key because standard drugs are basically like carpet bombing your system. You take a pill and it floods everything. This is a sniper shot.
A molecular sniper shot, yes.
Yes. So we have the storage, which is the DNA, and we have the courier, which is the virus or the AAV. Now we need the editor, the thing that actually sits down at the keyboard and changes the text. Enter CRISPR.
CRISPR-Cas9. By now, it's a huge buzzword. Most people have heard of it.
Yeah.
But it's often described as genetic scissors, which I think is a bit reductive.
Yeah, it implies it just cuts things up blindly, like you're making a messy collage.
Right. It is really a molecular text editor. It finds a specific string of text. Your DNA sequence verifies it matches the search query, and then it can cut, delete, or crucially paste something entirely new in.
And I want to pause here for a second because usually when we talk about this kind of stuff, it feels very science fiction 2050. But looking at the timeline in the source material, this isn't the future. This is happening right now.
It is already here. The big it's already here moment was December 2023. That was when the FDA officially approved Casgevy.
This is the sickle cell treatment.
Yes. And we really need to understand the gravity of this. Sickle cell disease is a horrific condition. A single-letter typo in the DNA causes red blood cells to turn into crescent shapes. Sickles.
And they get stuck, right?
They get stuck in blood vessels. It causes excruciating pain, organ damage, strokes. It is a life of unimaginable suffering.
And Casgevy just fixes it.
Casgevy uses CRISPR to edit the stem cells of the patient. It specifically edits a gene called BCL11A. In the clinical trials, the results were not just good, they were completely transformative.
How so?
29 out of 31 patients were completely pain-free for a year. We aren't talking about managing pain with heavy opioids. We are talking about rewriting the source code so the pain never happens in the first place.
It's not a treatment then. It's a patch.
Yeah.
A permanent software update for the blood.
Exactly. And that opened the floodgates. We have Luxturna for inherited blindness now, literally injecting a viral vector directly into the retina to restore vision. People are seeing stars for the first time in their lives. We have NTLA 2001, which is intravenous CRISPR for a fatal heart condition called amyloidosis.
They just inject that one into the blood.
Just right into the blood. It hunts down the liver cells and reduces the toxic protein by over 90%.
And what about that cholesterol one? CTX310. That one really jumped out at me because of the sheer scale of the problem. Heart disease is the #1 killer globally.
This is the one that might actually change public health on a massive scale. A single infusion. One shot. It permanently switches off a gene called ANGPTL3, the result. Cholesterol drops by about 50%.
Permanently.
Permanently. No more daily statin pills, just one genetic edit and you're done.
It really does sound like we are moving away from traditional medicine and moving into IT support for the human body.
That is exactly the shift the sources are describing. We are debugging the system.
So let's run with that debugging metaphor for a minute. If the body is a computer, how do we categorize the glitches we're trying to fix? The source material breaks this down in a really fascinating way.
Well, let's look at cancer. In this framework, cancer isn't a thing. It's a logic error. It is quite literally a corrupted loop.
Like when your browser freezes and the loading wheel just keeps spinning indefinitely?
Exactly like that. A normal cell has a strict program. Grow, divide, stop. Cancer just deletes the stop command. It creates a while-true loop. Grow, divide. And it consumes all the system's resources until the entire system crashes.
So how do you debug a loop like that?
The proposal here is something called the tri-mode nanite. This is where we get into truly programmable medicine. You design a viral nanite with 3 distinct operating modes. Mode 1 is seek and destroy.
Target acquisition.
Right. It identifies the cancer cells based on their specific genetic markers, the very mutations that make them cancerous in the first place. Once it gets inside, it delivers a kill switch. It triggers apoptosis, which is programmed cell death. It basically forces the cell to commit suicide.
But if you have a massive tumor and you suddenly kill all the cells in it, you just have a hole full of dead tissue, right? That seems dangerous.
Highly dangerous. That is why you need mode 2, which is restore. The nanite releases signals to activate nearby healthy stem cells, telling them to divide and fill the gap with healthy tissue. You patch the hole as soon as you clear it.
And mode 3?
Self-destruct. This is critical. You do not want these nanites floating around your body forever, potentially mutating or causing immune issues. Once the mission is complete, or after a strictly set amount of time, the nanite just deactivates. It breaks down. No trace left behind.
It's basically the perfect hit job. Clean, precise, and the assassin just melts away.
And we are seeing early versions of this right now with oncolytic viruses. These are viruses that specifically like to eat cancer cells. But they do something else too. They transform a cold tumor into a hot one.
Cold, meaning the immune system is just completely ignoring it.
Right. Cancer is very, very good at hiding. It puts up a biochemical do not disturb sign. That is a cold tumor. An oncolytic virus goes in and bursts the cancer cells open, spilling their guts everywhere. Suddenly, the immune system sees the mess and rushes in. It wakes up the body's own police force.
It basically blows the whistle.
Exactly.
Now, there was one part of the debugging section in the sources that felt, well, it felt almost magical. The structural frontier, using light to heal. This sounded like straight-up Star Trek territory to me.
Ah, yes. Photonic modulation. This is where biology meets quantum physics.
Like, please state the nature of the medical emergency, and then they just wave a blinking light over your arm.
It is honestly not that far off. We are talking about photonic band gap structures. Essentially, researchers are finding that light, specifically the geometry and frequency of light, can directly influence the shape of proteins.
Because proteins are essentially just folded shapes, right? Like biological origami.
Yes, their function is entirely determined by their geometry. Prions, for instance, which cause Macau disease or Creutzfeldt-Jakob disease, are terrifying because they are corrupted data types.
Right.
They're proteins that folded into the wrong shape, and they are highly infectious. If a prion touches a normal, healthy protein, it forces the normal protein to fold into the wrong shape, too. It is like a corrupted file that corrupts every single other file it touches.
And since they aren't bacteria or viruses, you can't just kill them with antibiotics. They aren't even alive.
Exactly. Standard drugs work by chemistry. They physically stick to things. But how do you drug a geometric shape? It is incredibly hard. But if you can use specific light frequencies to energetically destabilize the bad shape or encourage the good shape, you can fix the problem without any chemicals at all.
And there's actual hard science on this. It's not just a crazy theory.
There is. The notes mention a major study from July 2025, the PHOBIT system. They used light to suppress tumors in living tissue. They could turn the tumor suppression on and off just by shining a specific light on it. It is literally using light as code.
That is just wild. It redefines what medicine even looks like. But, okay, that is fixing what's broken. That's debugging. That's maintenance. But let's be honest here, the part of the notes that really got my imagination running was the next step, not just fixing, but upgrading.
Opening the library of nature.
Right. The whole concept here is that nature has been running beta tests for billions of years. It has solved problems we can't even begin to imagine. And the solutions are all stored in the exact same code we use.
Exactly. DNA is a universal language. The code that programs a tardigrade, or an owl, or a deep-sea fish is written in the exact same ATCG language as the code that programs you.
So can we just copy-paste? Like, can I just take the Eagle Vision file and drop it into my genome?
Well, not simple copy-paste, no. It's more like functional translation. If you take a gene directly from a tardigrade and put it into a human cell, it might not work. The grammar is slightly different.
Right.
But if you understand the function, what the protein actually does, you can rewrite the code to fit human biology. You keep the meaning, but you change the words.
So we aren't talking about stitching a salamander tail onto a human. We aren't making chimeras.
No, we aren't Dr. Frankenstein. We are software engineers. We are rewriting the code for human cells to produce the same biological result.
Let's look at the candidates in this library. My absolute favorite has to be the tardigrade. The water bear, these little microscopic guys, are indestructible.
They're easily the toughest organism on Earth. They can survive the vacuum of space, boiling water, absolute zero, and massive, massive amounts of radiation. And the secret is a single protein called DSUP.
Damage suppressor.
Correct. DSUP is a protein that physically hugs the DNA. It wraps around it like a microscopic protective blanket. When radiation hits the cell, the DSUP takes the hit, absorbing the energy and protecting the fragile genetic code underneath.
And we can actually use this.
We already have.
Yeah.
There was a landmark MIT study in February 2025. They didn't even edit the human genome permanently. They used lipid nanoparticles, the exact same tech used in the COVID mRNA vaccines, to deliver synthetic mRNA for DSUP.
So you basically just get a shot of tardigrade essence?
Essentially, yes.
Yeah.
And for a few days, those human cells were highly resistant to radiation. Imagine the practical implications. You're a cancer patient about to get aggressive radiation therapy. You take a shielding dose of DSUP. It protects your healthy cells while the tumor still gets fried. Then a few days later, the shield just wears off.
Or you're an astronaut going through a heavy radiation belt on the way to Mars. You take a pill and you're bulletproof for a week.
Exactly. It is temporary on-demand augmentation. You don't need to be permanently genetically modified. You just install the app when you need it and delete it when you're done.
Okay, next book in the library. The Salamander, the absolute master of regeneration.
The axolotl specifically. If an axolotl loses a leg, it doesn't just scar over like we do. It grows a blastema. This is a magical cluster of stem cells that knows exactly what to do. It grows bone, muscle, nerve, skin. A perfect functional replacement.
Why can't we do that? We heal, but we just scar. Why did humans lose that feature?
The prevailing theory is that it was a harsh evolutionary trade-off. For a warm-blooded human running on the savannah, an open wound is a death sentence. Infection kills you incredibly fast. So we evolved to scar, seal the breach fast and dirty, keep the bacteria out. But the axolotl lives in the water and has time. It can wait months to regrow a limb perfectly.
So we traded quality for speed, basically, to survive.
Exactly. But the new research specifically, that LSU study from 2024 and the major Harvard work from late 2025, suggests something really profound.
Yeah.
We might still have the code. It is just dormant, it's silenced.
And it's just commented out on our source code.
Yes, perfectly stated. And the Harvard study linked it to adrenaline. They found that the regeneration process is heavily linked to the nervous system, specifically adrenaline signaling. It creates a body-wide memory of injury. The body knows it is hurt, and it primes the entire system to rebuild.
So the goal is to create a nanite that wakes this dormant code up.
Precisely. A nanite that delivers transcription factors. These are chemical signals like PAC7 or FGF that act like switches. It tells the human arm stump, don't scar, reboot, run the grow arm program again.
That is, I mean, it's incredibly hopeful and maybe a little disturbing to picture, but mostly hopeful. What about the owls? We mentioned them earlier.
Vision. Owls have highly specialized opsins, which are proteins in the eye that are incredibly sensitive to low light and even infrared light. We could, in theory, deliver the genes for these specific opsins to human retinal cells.
So real biological night vision without needing heavy goggles.
Biological night vision, yes. And then there are the seals, deep-diving mammals. They have 30 times the myoglobin of humans. Myoglobin is what holds oxygen in the muscle tissue.
So if we borrowed that specific code...
You could hold your breath for 20, maybe 30 minutes easily. Think about stroke victims. If their brain tissue had that kind of massive oxygen reserve, a stroke might not be fatal. It would just be a temporary blip. Or think about deep-sea rescue divers.
It totally changes what it means to be human. We really are talking about programmable evolution.
And that brings us to the blueprint section. How do we actually build this? Because having the idea is one thing, engineering it is another entirely. The source material outlines a 5-layer platform.
Okay, let's walk through this architecture layer by layer. Layer 1 is the library.
That is the catalog we had just discussed. Identifying the traits, we need to sequence everything in nature to find the absolute best code available.
Then layer 2 is delivery.
That's the courier. Engineering the AAV to get to the exact right organ. You need a kidney delivery for a kidney problem. We need vectors that don't just get immediately eaten and filtered out by the liver.
Right. Layer 3 is the editor.
And this is evolving so fast. We started with CRISPR-Cas9, which, as we said, cuts the DNA. It's aggressive. But now we have base editing. That is swapping a single letter, an A to a G. Without ever breaking the DNA strand, it is much safer with far fewer errors. And there's also epigenome editing, which is like turning the volume knob on a gene up or down without actually changing the song itself.
Layer 4 is dynamic control. And this is the one that makes it feel like actual software programming to me, the if-then switches.
This is critical for safety. You do not want a growth gene effectively always on. That is just cancer. You want a synthetic promoter.
Yeah.
You code the DNA so the gene only turns on if a specific drug is present, or if a specific light shines on it, or if it detects a specific tumor marker in the vicinity.
So you literally build a logic gate. If tumor, then release poison.
Exactly. Biological logic gates.
And finally, layer 5, iterative augmentation.
This is the philosophy of software development applied to biology. You don't do it all at once. You do version 1.0, you monitor the patient, then you release an update, version 1.1.
It really is treating biology exactly like software development.
It is. And we have to contrast this approach with natural evolution. Natural evolution is completely random. It throws spaghetti at the wall for 1,000,000 years and just sees what sticks. It is cruel. It requires massive amounts of death to select the winner.
Survival of the fittest.
Right. Programmable evolution, on the other hand, is intentional. It is directed. It is incredibly rapid. We aren't waiting around for a lucky mutation. We are designing the feature we want.
Which brings us to the elephant in the room, or maybe the T-Rex in the room, considering what we're talking about. This sounds a lot like playing God, or at least playing senior developer with a complex system we really don't fully understand yet.
And that is the terror of it. Because all code has bugs. And when the code is your actual DNA, a bug isn't just a blue screen of death. It is a tumor, or something much worse.
So let's talk about those bugs in the system. What are the concrete technical dangers here?
The classic one is called off-target effects. You tell the editor to change a specific gene on chromosome 4, but the search function is a little fuzzy, and it accidentally snips something over on chromosome 12. Maybe it accidentally snips in a tumor suppressor gene. Oops. Now you caused cancer while you were just trying to cure blindness.
That is absolutely terrifying.
It is, though. Accuracy is improving exponentially with these newer base editors. But the bigger risk might actually be runaway expression. Let's say we successfully trigger that grow arm signal we talked about. But for whatever reason, the stop signal doesn't work.
You just keep growing arm stuff, like bone and muscle.
You get teratoma, a mass of completely disorganized tissue. Bone, hair, teeth, muscle, all just growing uncontrollably in a chaotic mass. That is exactly why the kill switch is not optional. It is a strict requirement. Every single nanite needs a self-destruct mechanism that can be triggered externally. If things go wrong, you pop a pill and the nanites instantly die.
There's also the immune system to worry about, right?
Right. Your body hates viruses, even helpful ones. If your immune system attacks the courier before it delivers the message, the therapy fails completely. Or worse, you get a massive, deadly inflammatory reaction. That is why researchers are constantly looking at stealth vectors, coating the virus in lipids or proteins that essentially make it invisible to the immune system.
But beyond the technical hurdles, there is the societal impact, the ethical architecture of all this. You mentioned earlier that Casgevy costs $2.2 million.
Yes. That is the current price tag for a single patient.
So let's play this scenario out. If we have the ability to literally upgrade humans, better memory, stronger bones, radiation resistance, night vision, who actually gets it? Does Jeff Bezos get to live to 150 with perfect health while the rest of us just die at 80?
That is the ultimate nightmare scenario, biological inequality. We are already fiercely divided by wealth. Imagine if we were permanently divided by biology, a literal species split between the enhanced wealthy who never get cancer and have superior cognitive function, and the baseline poor who still suffer from ancient diseases.
It creates a permanent caste system written directly into our DNA. I mean, Gattaca wasn't supposed to be a documentary.
Exactly. That is why the experts in these sources argue strongly that enhancements must be treated as public health infrastructure, not luxury goods. Like vaccines. If it works, everyone gets it. Otherwise, you fracture the human race into two entirely different species.
And then there is the massive question of lineage. Somatic versus germline editing. We need to be very, very clear about this distinction for the listeners.
It is the absolute ethical line in the sand. Somatic editing means editing your body, your specific adult cells. If you get a CRISPR edit to fix your heart condition and then you have a child later, your child does not inherit that edit. It dies with you.
Okay. That seems much safer. It basically limits the blast radius if something goes horribly wrong.
Exactly. But germline editing means editing embryos, sperm and eggs. That edit is permanently passed to your children and their children and their children forever. You are actively changing the future of the human gene pool.
And this actually happened already, right? In 2018?
Yes. He edited twin girls as embryos to be naturally resistant to HIV. The global scientific community exploded in outrage. He was widely condemned. He was jailed, and rightly so, because we simply do not know nearly enough about the source code yet to be making permanent, irreversible edits to the human lineage.
It's like pushing a beta software update to the entire global internet without testing it. If there's a hidden bug, you crash everything permanently.
Exactly. The expert consensus right now is a strict moratorium on germline editing. Do not touch the embryos. But somatic editing, especially reversible types like the mRNA DSUP we talked about. Proceed, explore it, heal the suffering person right in front of you. Just don't rewrite future generations until we truly understand every single line of the code.
So where does this leave us at the end of all this? We have gone from viewing viruses as our ancient enemies to seeing them as our couriers. From DNA as a deep mystery to DNA as a literal hard drive.
We are witnessing a profound philosophical shift. For all of human history, medicine has been about treating the body, fixing it after it breaks. We are now moving to designing the body.
The body just isn't a fixed vessel anymore. It's a platform.
It's a platform for updates. We're picking up the quill to actively write our own biology, and that is a staggering responsibility.
It really makes you think. The code of life isn't sacred just because it's unchangeable. It's sacred because it's ours.
And we are finally learning to read and write it for the very first time.
I want to leave you, the listener, with a thought today before we wrap up. We talked a lot about the Library of Nature today. The tardigrade's radiation shield, the owl's eyes, the salamander's arm. If you could download just one trait, if you could install one single app from nature into your own body, what would it be? And more importantly, if we're treating the body like software, what happens when someone figures out how to hack the update?
Oh, computer virus for your actual biology. That is the question of the century.
Thanks for diving in with us today. Keep exploring, and we will see you on the next Deep Dive.